variations on a theme, and we are looking at the theme of Minimax, one player versus another player, in scenarios where it's purely strategy-based and not luck-based. Let's have a look at 3 of those problems and go through them one by one. 913 Cat and Mouse, flagged as hard. A game on an undirected graph is played by 2 players, mouse and cat, who alternate turns. The graph is given as follows. Graph A is a list of all nodes B, such that AB is an edge of the graph. Mouse starts at node 1 and goes first. Cat starts at node 2 and goes second. And there's a hole at node 0. During each player's turn, they must travel along one edge of the graph that meets where they are. For example, if mouse is at node 1, it must travel to any node in graph 1. Additionally, it is not allowed for the cat to travel to the hole node 0. The game can end in 3 ways. If ever the cat occupies the same node as the cat, like if mouse and cat occupy the same node, the cat wins. If the mouse reaches the hole, the mouse wins. If ever a position is repeated, the game is a draw. Given a graph and assuming both players play optimally, return 1 if the game is won by mouse, 2 if the game is won by cat, and 0 if the game is a draw. Look at example number 1. Input 2, 5, 3, 0, 2, 0, 4, 5, 1, 4, 5, 2, 3, 0, 2, 3. Output 0. With the explanation 1, 3, 4, 2, 5, 0. And that apparently means that the game has become a draw, since the mouse and cat can always evade each other, so to say. They can always go to places where they can make one more move from each other. Next up is predict the winner, medium 486. Given an array of scores that are non-negative integers, player 1 picks one of the numbers from either end of the array, followed by the player 2 and then player 1, and so on. Each time a player picks a number, that number will not be available for the next player. This continues until all the scores have been chosen. The player with the maximum score wins. Given an array of scores, predict whether player 1 is the winner. You can assume each player plays to maximize his score. So we can see there's a theme already. There's like this strategic aspect to it, where both players purely want to follow a strategy to win without luck and without forcefully trying to lose or to play random. Example 1, input 1, 5, 2, output false. Explanation. Initially, player 1 can choose between 1 and 2. If he chooses 2 or 1, then player 2 can choose from 1 or 2 and 5. If player 2 chooses 5, then player 1 will be left with 1 or 2. So the final score of player 1 is 1 plus 2 equals 3, and player 2 always has 5. Hence, player 1 will never be the winner, and you need to return false. Input 1, 5, 233, 7. True. Player 1 first chooses 1. Player 2 has to choose between 5 and 7. No matter which number player 2 chooses, player 1 can choose that big number, 233. Finally, player 1 has more score, 234, than player 2, 12. So you need to return true, representing player 1 can win. The third one, stone game, 877, scored as medium. Alex and Lee play a game with piles of stones. There are an even number of piles arranged in a row, and each pile has a positive integer number of stones, called piles EI. The objective of the game is to end with the most stones. The total number of stones is odd, so there are no tiles ever. Alex and Lee take turns, with Alex starting first. Each turn, a player takes the entire pile of stones, from either the beginning or the end of the row. This continues until there are no more piles left, at which point the person with the most stones wins. Assuming Alex and Lee play optimally, here's our theme again. No luck, no torpedoing the game. Return true if and only if Alex wins the game. Example 1, 5, 3, 4, 5, representing those piles of stones. True. Explanation: Alex starts first and can only take the first 5 or the last 5. So he takes the first 5, so the rule becomes 3, 4, 5. If Lee takes 3, then the board is 4, 5, and Alex takes 5 to win with 10 points. If Lee takes the last 5, then the board is 3, 4, and Alex takes 4 to win with 9 points. This demonstrated that taking the first 5 was a winning move for Alex, so we return true. Okay, let's go to the underlying theme, which is explained in great length with very interesting backstory at towardsdatascience.com by Marissa Epps in 2019, called Game Theory, the Minimax Algorithm Explained. And she goes on to explain the whole backstory of how Deep Blue leveraged this approach to beat the then world champion Garry Kasparov in 1997. Searching optimal solutions along a tree of potential moves and potential next moves in order to find which is the current best move to make. And in doing so, the tree would be interestingly be able to be labeled in like 2 different categories. Like one level would be the category where we ourselves make a move, and then the next level would be all the moves that the opponent makes, assuming that the opponent has the same strategy as ourselves to win the game and to not forfeit the game or not play random. And then the next level underneath would be our own move again. And you can basically assign a score to how good your move is, or how well your move will turn out for further moves, or like for your own, let's say for your own utility, they call it, for your own utility, like how useful is that move at that level. And then how useful will be an opponent's move at the next level. And the opponent, of course, wants to kind of like maximize their utility, thereby diminishing your own utility. And you would have to assume that the move that the opponent makes at that level will be the best for him, which means the move will be the worst for you, so like the minimal utility at that level. But then at the next level underneath, it's your turn again. You can make the best move, the maximum utility. And then combining those antagonal aspects, making a maximum move, and then searching which is like the minimal move that your opponent will make then, and respond to it by making your maximum move, will result in this paradigm of making minimal, maximum moves until you hit like a game-ending point in your graph, or you hit your maximum level of like tree depth in which you want to explore the tree, and find what's the value there, and then return this back. And the approach in which to traverse the tree usually is assigned to also be like, I think, a depth first search approach, where you just like first call again and again and again before you continue with your operations. And since it's minimize, maximize, you have to like divide your algorithm into like 2 parts. One part being the your own maximize part, and then the other part is like the opponent's part, which is like where your score gets, or your utility gets, minimized. So one aspect calls the other aspect, and then the other aspect calls your aspect. which then ends up being this dual antagonistic approach. Really, really great to go through and to like study up on all the details, and it comes with like some nice graphics on how the details work. But the key thing basically to look in for all the key thing that we now look for in the implementations and algorithms that solve those three problems is to find this aspect of a line in the code that maximizes the score, and then calling another line in the code that minimizes the score, and then maximizes the score again. That's the key thing that we will be looking for, the variations of our theme. Okay, cat-mouse game, which is again first set up, it's being called, and there's vector initializations going on. Most of the time, you'll find that there can be a very efficient implementation of finding a solution using a dynamic programming approach, which is basically a bottom-up approach where you first fill in some sub-levels of your array and then expand on them to fill the rest of your array. Nonetheless, you'll do this here in a minimal maximal fashion, which I can outline in the game helper function, where it does next move for the mouse and next move for the cat, and it calls them, the current is going to be the minimum for the cat max move, and then the current is going to be a maximum if the mouse max move. And here this dual recursive call is basically implemented in two for loops that run and call each other, so to say. And the dynamic programming aspect here becomes evident in this two-dimensional array of mouse and cat moves, dp, which is then filled up from a starting point up until an end point. And once that endpoint has been filled up, we know if that game resulted in a win for the mouse or a win for the cat. Specifically here, since our graph of move options is limited, as opposed to a graph of move options on a chess, let alone Go board. Next up is predict the winner. That was in a game of choosing numbers. And here, searching for the variation of our theme of min and max, is we have our two for loops here. We also have a bottom-up approach where a dynamic programming array of two-dimensional size is filled and started from a starting point and then like gradually being filled up. And at whichever point in the array we find out which player is it. Is it the player number 1 or the player number 2 with this auto function here? We will then call either minimize the utility or maximize the utility, depending on if it's your own player or the antagonistic player. And depending on that both want to perform a strategy that results in a win for themselves, we can make leverage of this Minimax approach. And then at the end, once we've iterated over all elements in the array in order to fill up the array in a dynamic programming fashion, we just query that array element. That's the one that tells us which winner is it going to be, right? Last one is the stone game. That again comes with like a really nice explanation. Basically, in words, it also does a dynamic programming approach, and then it goes like if A picks piles I, the rest of the piles is left, so B can pick either piles I plus 1 or piles J. So like the two outermost parts of the pile, leaving A to then choose in the dynamic programming array, which is then filled up iteratively. And B will try to maximize its own output, make you choose your minimal value, etc. And the corresponding function to fill up your dynamic programming array then shows this min-max behavior. Find a min here, find a min here, find a max out of these two situations, and fill your dynamic programming array accordingly. And we see that in the code exactly here and here we have the min condition for the antagonistic player, and then we have the max condition for our own player. Like after opponent player made a move, we make our move and accordingly fill in the corresponding part in the dynamic programming fashion for the array. And at the end we will find a condition. This is a condition that says, okay, if we have more than half of the entire sum of the elements, more than half of the entire sum of the stones, that means we have won. There's no way for the opponent to win this game if we have more than half of the stones. And that's what this whole conditional expresses. And the return value will be either true, means we won, or false, we lost. And that's all to it. That's all to the min-max approach that can be used for as simple as a stone or cat and mouse game, and if implemented well and executed well, can be used to beat a chess world champion in 1997.